So let's continue on with probability. Let's start with some vocabulary. A probability experiment is an activity involving chance. A trial is each repetition of the experiment. An outcome is each possible result of the experiment. Event is a set of outcomes. And then lastly, sample space is the set of all possible outcomes. So lots of vocabulary here with probability that we will use interchangeably. When all outcomes are equally likely, we can calculate the theoretical probability of event A in the sample space by computing. This says probability of event A would be the number of outcomes in the event out of the number of outcomes in the sample space. So outcomes in the event that you are looking for it to occur out of total number possibility in the sample space. Let's look at an example. The numbers 1 through 30 are written on slips of paper that are placed in a hat. Students draw a slip to determine the order in which they will give an oral report. Event A is being one of the first 10 students to give their report, or in other words, the students that drew numbers 1 through 10. Event B is picking a multiple of 6, so students that draw a multiple of 6. If you pick first, calculate each of the indicated probabilities. So just for reference, let's list out all of our possible events for a probability of event A being the first 10 students. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. If I drew one of those numbers, I would be going in one of the first 10 in giving my oral report. And event B, multiple of 6, 6, 12, 18, 24, and 30. So number one, P of A, so that's how shorthand way of how to write the probability of event A occurring. So there are 10 possibilities in event A. Out of the total sample space, there are 30 slips of paper. And yes, we can reduce that down to 1/3. Number 2 says the probability of A union B. Do you recognize that symbol there? That is union. It can also be written as A or B. So be very comfortable with that because they are going to use both here. So we are looking at the union of event A and B together. So we're going to add them all together. In event A, we have 1 through 10, and then union. So everything all together plus event B. We already counted 6. I'm not going to count it again, but we had 12, 18, 24, and 30. So we had 10 possible outcomes in event A, 4 more from event B. So we have 14 out of a possible 30. You can reduce that down to 7/15. Number 3, we have the probability of A intersection B, which can also be written as A and B. This is what they would share in common. Looks like they share a 6 and only a 6 in common. So we have one possibility out of 30 that they share in their intersection. Number 4, the probability of A complement, so not in A. We've got 1 through 10 is in A. That would mean 11 through 30, or there are 20 values out of 30 left over, and you can reduce that down to 2/3. The sum of the probability of an event and the probability of its complement, which we can note here, probability of A plus the probability of A complement, is always 1. We can see that if I take the 1/3 from the probability of A and add it with example number 4, the complement of A was 2/3 equals 3/3 or 1. Moving on, 2 events are mutually exclusive if they cannot both occur in the same trial of an experiment. They are completely separate. Mutually exclusive means they are separate and they do not share any outcomes. For example, if I'm rolling a number cube, that would be like rolling a 3 and rolling an even number. I can do either of those and they don't share any outcomes together. Rolling a 3, rolling an even number, 3 is not even, so they don't overlap or share any outcomes. Another example, playing with a deck of cards, I can draw a black card or a red card. Two separate events. They do not overlap. They don't share any outcomes in common. It's either black or red. There's not any cards that are black and red. So to find mutually exclusive events, if A and B are mutually exclusive, then to find that probability of A or B happening, you're just going to add those probabilities together. So whenever you see the word or, I want this or that to happen, I want the probability of rolling a 3 or rolling an even. If you see the word or in your probability, that means you're going to add those probabilities together. Just a little memorization tool. So our example here, a number dodecahedron has 12 sides and is numbered 1 through 12. So much cooler than a number cube with just the 6 sides. Dodecahedron has 12 sides, 1 through 12. Number 5, what's the probability that you roll an even or a 7? So I'm going to note that here as probability of even or a 7. So what's the probability of rolling an even? Let's list out our possibilities. We could roll a 2, 4, 6, 8, 10, or 12. And the probability of rolling a 7, well, there's only a 7, 1, 7 on that dodecahedron. So let's add those probabilities together. Probability of rolling an even, there were 6 possibilities out of 12. Plus, because we are finding an or, I want even or a 7, add those probabilities together. Rolling a 7, there is 1 7 out of 12, add those probabilities together, 7 out of 12, probability of rolling an even or a 7. Number 6, what's the probability you roll a prime number or a 6? So I'm going to note that here, probability of a prime or 6. So what would be our prime numbers? On a dodecahedron, we would have 2, 3, 5, 7, and 11 are all prime numbers. And then the probability of rolling a 6, there is just, well, a 6. So let's take those probabilities and add them together. Rolling a prime, there were 5 possibilities out of 12. It's an or, so I'm going to add those probabilities together. And then the probability of rolling a 6, there's 1 6 on that dodecahedron. That's going to give us a 6 over 12, or you can simplify to 1/2. Probability of rolling a prime or a 6 on a dodecahedron, 1/2. Now our next vocabulary is two events are overlapping. Events if they have one or more outcomes in common. I was referring to this vocabulary a moment ago describing mutually exclusive events. Here we have overlapping events where they do share outcomes in common. For example, rolling that number cube if you wanted to roll a 4 or an even. So there's the possibility of rolling a 4, but then when you can include rolling an even, they're going to be sharing that possibility of rolling that 4 in both of those probabilities. In your deck of cards, if you were going to draw a black card or draw an ace. So our aces are for each of our 4 suits. 2 of our suits are black, and so as you look for drawing an ace, there are black cards that are aces, and so those would be overlapping. So if you do have overlapping events, then the probability of finding A or B happening, you're going to still add them. I'm not changing my memorization tool. When you have an or, you always add, but if they are overlapping, you need to subtract away the overlap, the things that they share in common, their intersection. So make a note here, we are going to subtract the overlap. Very important right there. Subtract, so still add probability A with probability B, but then we're going to subtract where we've overlapped or where we've double dipped, where we have counted the same outcome twice. So let's look at an example. Number 7, there's a spinner with 15 equal areas numbered 1 through 15. If the spinner is spun one time, what's the probability the result will be a multiple of 4 or a multiple of 3? Let me give myself a little notation here. We're going to do multiple of 4 or multiple of 3. So multiples of 4 on this spinner, would it be 4, 8, and 12? Multiples of 3 on our spinner, we're going to have 3, 6, 9, 12, and 15. Now notice they overlapped, right? There are 12s in each of those lists. So we're going to take our probability of A and add it with our probability of B, but because they are sharing outcomes, we need to subtract that overlap of A and B. Our probability of A, there were 3 out of 15 sections. Our probability of B, there was 5 out of 15 sections. And then we are going to subtract away that one outcome that they're sharing in common, the 12. Subtract one possibility, the 12, out of 15. So we have 3/15 plus 5/15 minus 1/15. Because if I count these all up, if I'm counting 12 twice, there's not 2 12s on the spinner. There's not twice as much chance of spinning a 12. There's only one 12 on the spinner. So if I left it the way it was, my probability would be showing as if there was 2 12s to select. All right, so we got 3/15, 5/15. That makes 8/15 minus 1/15, 7/15. Final answer. Number 8, in a certain Algebra 2 class of 27 students, 11 of them play basketball and 10 of them play baseball. There are 8 students who play both sports. What is the probability that a student randomly chosen from the class plays basketball or baseball? So we got probability of basketball or baseball. They gave us lots of information in here. You can notice on number 8 and also in number 9, very similar problems. I have bolded on this problem who play both sports. These are directly from Delta Math. Delta Math does not bold that statement for you, but I do want to show you number 8 and then number 9 are very similar except the wording right there. So our problem right now, number 8, says there are 8 students who play both. So if I counted up all the students who play basketball, hey class, everybody raise your hand if you play basketball. 11 students raise their hand. Okay, class, hands down, hands down. Who plays baseball? And 10 students raise their hand. Well, in that process, the 8 students who play both, they raise their hands both times, right? So let's look at it over here. We've got basketball. There were 11 out of 27 in the class that played basketball. Baseball, we had 10 out of 27 of the class. And then we had 8 students that played both. So we've got probability of A, basketball, plus probability of B, baseball. And then we've got to subtract the students that play both, A and B. Okay, so we've got 11 over 27 plus 10 over 27. Who played both? 8 out of 27. Simplify, and we are going to get 13 out of 27 is the probability of students who play basketball or baseball in this Algebra 2 class scenario on number 8. Number 9 is very similar. In a certain Algebra 2 class, there's 27 students. Now, not every Delta Math problem is 27 students. Read those numbers very carefully. 18 of them play basketball, 16 play baseball. There are 3 students who play neither. Again, Delta Math does not bold this right here. I did to show you there are 2 types of problems worded very similar. 3 students play neither sport. Hey, class, everybody raise your hand if you play basketball. 18 students. All right, put your hands down. Raise your hand if you play baseball. 16 students raise their hand. There's 3 students that didn't raise their hands at all. Cool? So what's the probability that a student randomly chosen plays basketball or baseball? Same question. Okay, so basketball, I'm going to use the same notation here. Basketball, we had 18 out of 27. Baseball, we had 16 out of 27. And let's also list here neither. They told us that we have 3 out of 27 students that play neither sport. So if I'm looking for students that play basketball or baseball, and I really don't care if they play both, I just want to know, of all my students in the class, what's the probability that I pick a student that plays basketball or baseball? These problems kind of make me laugh, and they kind of drive me crazy on Delta Math, because if I care about all the students that play basketball or baseball, and I told them, hey, if you play basketball or baseball, go stand on the left side of the room. Who would not be standing on the left side of the room? The 3 students that play neither. You see that? So I have a love-hate relationship with these questions on Delta Math, because I'm going to take the 27 students total minus the 3 that play neither. They don't play basketball or baseball. And there's 24 students that play basketball or baseball, maybe both. So we have 24 out of 27 students that play basketball or baseball. So this is kind of like I said, a kind of silly question that Delta Math has. It does require you to think and evaluate and really digest the situation. You have 3 students that play neither. Therefore, those 3 students do not play basketball or baseball. So I just subtracted 3 from 27 to give us 24 students that do play basketball or baseball or maybe both out of the total class 27. All right, number 10, we are going to switch gears and we are going to focus on just the formula alone for overlapping events, where if you're looking for A or B, it's that probability is equal to the probability of A plus probability of B minus that overlap, right? A and B. And so we're going to take the information that they provided us. Sometimes they provide us too much information. You're not going to use every value, but we're going to find the value that they are requesting. On number 10, we are going to find the value of A or B. So that's what I've got here at the front. To find the probability of A or B, I need to take the probability of A, they said was 0.25, plus the probability of B was 36 hundredths, and subtract A and B, they also gave me that, subtract the 0.2 would give me the probability of A or B. You can throw all of that in the calculator and we are going to get 0.41. Probability of A or B, 41 hundredths, using the information that they gave us and just utilizing the formula for overlapping events. Number 11, we're going to do the same thing. They've given me the probability of A, probability of B, probability of the intersection. Now, what is that? Probability intersection right there. That's and. Intersection is and. Find the value of probability of A union B. That's A or B. So let's rewrite it a different way. Our formula we can write as, instead of A or B, that's our union, A or B. A union B is equal to the probability of A plus probability of B, and then subtract the overlap, A intersection B. All right, we are looking for that A union B, or I could refer to it as A or B. So I'm going to plug in the probability of A, they gave us 44 hundredths, plus probability of B, they gave us 6 tenths, minus the intersection, the overlap, the and, is 394 thousandths. That's going to give me the probability of A union B is 646 thousandths. Final answer. And last one, number 12. Let's see, we were given A, we were given B, we were given A or B, and we're looking for and. Now this is a little bit different, right? So our probability of or A or B is equal to the probability of A plus probability of B, and then we subtract the and, right? So on this problem, I know the or, 0.2. I know that probability of A is 6 tenths. I know the probability of B is 45 hundredths, but I'm missing that probability of A and B that they want me to find. So we're just going to have to kick it in gear and do some equation solving. So we have 0.2 equals 1.05. I'm going to solve for the probability of A and B just like an equation. I'm going to subtract this 1.05 from both sides. Gives me negative 85 hundredths is equal to negative probability of A and B. Now we've got negatives on front of both of those, so I could divide both sides by -1, but we will get a positive 85 hundredths is equal to the probability of A and B. Final answer. So as is the case usually with probability, lots of vocabulary. We looked at our vocabulary words at the beginning. We reviewed finding theoretical probability. You just take the number of outcomes that you're considering in your event out of total numbers from a number of outcomes from your sample space. We also talked about mutually exclusive. Now your Algebra 2 standard is more about the overlapping events, where you need to subtract the overlap. So we needed to talk about mutually exclusive to illustrate how overlapping events occur. Just if you are looking for this or that to happen in a probability, you are going to add them. If they share any outcomes, you've got to subtract that overlap, guys, or you are double dipping and you are saying that there is twice as many chances of getting that overlapping. Like our spinner on number 7, there's not two 12s on the spinner, there's one 12. So it doesn't have a double chance of getting landed on. It has an equal chance of all the other numbers, just the fact that we're looking for a multiple of 4 or a multiple of 3. It showed up twice in our sample spaces. But be sure you are subtracting those overlaps. And then those last 3, we just hyper focus on the formula, making sure that you can recognize some of those notations, the union or the intersection symbol, which can also be interchanged with and or. So make sure you're practicing that. I tried to give you all a heads up last lesson. Learn your probability symbols because we are going to keep using them, and I don't want that to be a hiccup for you. So practice those, guys, and I'll see you in class.